Hi class. So we're starting 16.2 entropy. So at the end of this video, you should be able to define entropy, explain the relationship between entropy and the number of microstates, and predict the sign of entropy, which is delta S, for chemical and physical processes. So what are the factors that affect whether a reaction is spontaneous? Well, last section we talked a little bit about enthalpy, and we introduced entropy. So remember, enthalpy, right, is delta H, and we're dealing with heat or energy. And delta H is equal to H final minus H initial, which means that we're looking at the energy of our products versus the energy of our reactants. Well, entropy is the same thing, but entropy deals with randomness and disorder as opposed to heat. Right, but we need both factors. We have to consider the sign for both factors when we're trying to determine whether a reaction is spontaneous or not. So, the more disorder, the more random the reaction, the higher the value for delta S. And so delta S is also we're looking at the randomness of your products versus the randomness of your reactants. So the universe loves disorder. All right, so a high delta S is favorable for most spontaneous reactions. So spontaneity is favored by an increase in entropy. You do not have to memorize both of these equations. I just have these equations here so that you can, sorry, messed that one up. So I just have these two equations here so that we can look at the relationship between S and W. So we're comparing entropy with microstates. And so W means the number of microstates that are possible in a given situation. So think of W as ways. The more ways that you can make a system, the more random it's going to be, and I'll explain what that means. So let's say that we have two boxes and you have four particles. How many ways can we distribute those four particles between those two boxes? And so one way of doing it is, if you look at A, having all the particles in one box, in box one. The second way we can look at this, or the second way we can have those particles, is putting all of them in box B, like this. Another way that we can arrange the particles is to have three of them in one box, right, and one in the other, or vice versa, having one in the first box and three in the other. But the way that's going to give us the most distribution of particles, or the one that's going to provide the most number of microstates, is going to be C, where you have a distribution, an even distribution of two particles in each box. And so there are 6 different ways that you can do that, right? So the more ways, or W, that you can create a system, the more random it is, or the more probable that system will occur. So again, there are 5 possible distributions for this system, right? Again, the first one having all the particles in box 1, the last one having them all in box 2, having 3 of them in one box and 1 in the other, or having 1 in the first box and 3 in the other. But the one, again, that's going to give you the most distribution of particles is going to be C. Right? And so C will be the most probable. The most probable distribution has the largest number of microstates. So again, this equation is here only because we need to understand the relationship between W and S. And remember, S is entropy. And so they're directly related. If we increase the number of microstates that we can create, then delta S will also increase. So states of high entropy are favored because they are the most probable. So the most probable distribution has the largest number of microstates. Again, if we were looking at both of these systems, right? This is a non-spontaneous system, right? Because we've opened the valve, but all the particles are staying to the left, where they're more restricted, right? So this takes work for all those particles to stay and not to disperse, right? But the universe loves disorder, so spontaneously, what will happen is when you open that valve, some of the particles will go over into the other side. And so this would be a spontaneous reaction on the right. Non-spontaneous, again, you're forcing those particles to remain close together even though there's so much open space here. That requires work because those particles are going to naturally want to spread out. So as I stated earlier, entropy is another state function like enthalpy. State function meaning we're looking at products and reactants, not how the reactants became products, and not the between. We're looking at the final state minus the initial state. And so delta S of your system is equal to S of your final minus S initial. So there are 4 factors that influence entropy. The first is the phase of the substance. Is it a liquid? Is it a solid? Is it a gas? And so systems that are gaseous, right, those molecules are moving freely. There's more disorder. There's more randomness in a gaseous phase. So the sign for delta S for a gas is going to be higher than that of a solid. In solid state, remember those molecules aren't moving freely. They're in a frozen state. And so there's low delta S. So whenever you have order or the structures are in a solid frozen state, the sign for delta S is going to be small. So how does temperature affect entropy? It only affects entropy in that it determines what state a substance is in. So again, if you take a cup of ice out of the fridge, right, out of the freezer, and you put it on the counter, the ice is going to melt, right? And so your system, which is the ice, is going from a solid state to now a liquid state where its molecules are now moving more freely. So when you melt something, you are actually increasing entropy. And so the sign for delta S will be positive. So temperature is only an influence in that it affects the phase that your matter is in. This is a reiteration of what we saw a little bit earlier, but this is a model of heat. Right, so we're looking at heat, which is the red box, AB that contains AB, and CD is a cold box. So heat flows from high temperatures to low temperatures. But how many ways, and let's say that heat is represented by those 2 asterisks. How many ways can heat transfer, or can you have heat between those 2 systems? Well, in A, we're keeping all the heat in one box. In C, we're transferring all the heat to the other box. But B is what we actually see with the dispersal of energy, right? Heat's going to flow from hot to cold until both their temperatures are the same. So heat doesn't leave. So like if you're when you transfer heat, some of the heat remains in the first box, in the hot box, but some of the heat's going to flow into the colder box, and that heat's going to keep going back and forth between both boxes until they reach the same temperature. And so B is the most probable way that heat is going to move. And this picture is again just showing you the number of ways that 4 particles can be distributed between 2 boxes. So this is why delta S increases as you go from a solid to a gas. Look at the particles on the right. The particles on the right are bouncing off one another. Those molecules, there's more disorder, there's more randomness, and so you have a high delta S for gaseous phases. Solid states are going to have the lowest delta S because those molecules are ordered and they're not allowed to move freely. And so they have a lower delta S. And then a liquid is between both gas and solid. So there's some movement, but not as much as you have with the gas. Again, we're looking at the effective temperature on entropy, and again, it's mostly due to phase changes. So temperature only plays a role in this, in that it affects the state that our matter's in. So if we have high temperatures, you're going to have high kinetic energy, and if it's high enough, you'll move those forms, the matter, from solid to liquid state or liquid to a gaseous state, increasing delta S. So these are the other 2 factors that influence entropy. So we said the phase influences entropy and temperature, and this is supposed to be 3 and 4, but I put 1 and 2. So the third is the type and number of particles that make up a substance. For example, for atoms, heavier atoms possess greater entropy than lighter atoms. Why? Because larger atoms have more mass, there's more electrons, so again, there's more interaction between subatomic particles and movements of those electrons. For molecules that have more atoms in them are going to have more or a higher entropy than molecules that have fewer atoms. Again, you have more interaction, more movement. The fourth factor that affects entropy or influences entropy is variations in the type of particles. So substances that are pure versus mixtures. Compared to a pure substance in which all particles are identical, entropy of a mixture of 2 or more different particles increases entropy. And this is because of the additional orientations and interactions that are possible in a system comprised of non-identical components. So if we look at helium, hydrogen gas, and water at the bottom, right, which of those is going to have the highest entropy? Water, because it is a molecule that contains 2 or more atoms. Helium is going to be the hydrogen, H2, is going to be the second highest because it's comprised of 2 atoms. And helium is going to have the lowest value of entropy when comparing these 3. Even though helium and H2 have the same mass, because H2 has more atoms and there's more interactions between multiple atoms, it's going to have a higher entropy. So example 16.3 in the book asks you to predict the sign of delta S and then indicate the reason for your prediction. So let's say you have 1 mole of liquid water at room temperature, and then you increase the temperature of that water to 50. What's going to happen to the sign of delta S? It's going to be positive, right? It's going to increase because you're heating up the water, right, which increases kinetic energy, and so the sign for delta S is going to be positive. For B, we're looking at silver chloride in solution, and we're forming silver chloride solid. What's happening to the sign of delta S? It's decreasing because we have these ions that are freely moving in solution, and now you've put them in a solid state where they're not allowed to move anymore. And so you're decreasing the entropy of that system. For C, we're going to be looking at the gas phases. So in this case, we have 15 moles of O2 gas compared to 6 moles of CO2. You're decreasing the number of moles of gas, and so because you're decreasing the number of gas particles that you have, you're actually decreasing the sign of delta S. And finally D, ammonia solid is transformed to ammonia liquid. You're increasing the sign of delta S because, again, you're going from a solid to a liquid where those molecules are now allowed to move a little bit more freely. I hope that was helpful. I'll see you on Friday. Have a great day.